In this lesson, we're going to learn about graphs. Graphs give us another way to represent relations between entities. So in a graph, we have a representation of pairwise relations between objects. And the objects are represented as nodes in our graph, and the relations or relationships between those objects are represented by edges of the graph. And we'll see some examples of what graphs look like and how they represent data in this lesson. But how do we use them? Well, graphs are a very useful data structure. We can use them to represent all sorts of things that we encounter every day. We could use it to represent maps, so roads connecting cities or towns or locations. We can use them to represent links between users in an application like connections in Facebook or Instagram or LinkedIn. We can use them to represent websites connected by hyperlinks or computers connected over a network. We can use these graph representations to solve problems about these types of datas or situations. For example, finding the shortest path from one location to another location. So maps applications that we use to navigate that tell us the shortest path or the fastest path or paths without toll roads. All of those types of programs are using graph representations of data in order to make those calculations. Finding the optimal path over a network between two computer systems is another type of application that would use this type of data model to solve those problems. Graphs are used to rank pages by search engines. They're used to route network traffic. They're used to suggest the best route on roads and navigation software. There are so many applications of graphs and graph theory to solve problems in computer science, and that's why we're going to learn about this very important data structure. We're going to start by looking at some terminology and types of graphs. So here on this screen, we've got two graphs. So we can see that we have nodes in our graph. So these nodes represent some piece of data. This could be computers on a network or cities connected to each other by roads. It could represent any of those scenarios that we just mentioned. And the edges between the nodes represent that there's some relationship between those nodes. There's some sort of connection between these two pieces of data, or ways that these two pieces of data relate to each other. So this first type of graph we call an undirected graph, and it's undirected because there are no arrows basically on the edges. And what that means is that we can go in either direction. So from node A we can get to node B directly, and from node B we can also get to node A directly. And likewise we can go from A to C or C to A, and from C to D or D to C, and from B to D or D to B. We can move in either direction along each of the edges, and that gives us an undirected graph. The second example, we can see that there are arrows on the edges, and these arrows indicate the directions that we're allowed to move along the edges. So for example, in this graph, we can go from A to B, and we can also go from B to A because we have a directed edge in both directions. However, we cannot go from A to C because there is no edge in that direction. We can go from C to A, but not from A to C. So when we see arrows on the edges, this is called a directed graph, and the relationships are explicitly noted with these arrows. In these two examples, our edges don't indicate any values, and so either the values, the cost of moving along those edges is irrelevant, or perhaps it's the same in all cases. We can also have something called a weighted graph, and in a weighted graph we assign values to the edges and they can be considered when we're finding some sort of optimal path. So these values will represent some sort of cost. It could be a representation of distance or of speed or of resistance if we're talking about currents or electrical networks. It could represent something else that would cause some sort of lag between on the edge between the two nodes. So some sort of relative cost is represented in these weights. So if we looked at what we have here, this edge from A to B has a weight of 2, and the edge from A to D is twice as costly. It has a weight of 4. So it costs twice as much to go from A to D as it costs to go from A to B or B to A. So this is an example of a weighted, undirected graph because there are no arrows and there are values associated with each edge. We could also have a weighted, directed graph if we have arrows on the edges. Some types of graphs have particular characteristics. One example is a tree. A tree is an undirected graph in which two vertices or nodes are connected by only one path, and every child node has only one parent. So if we look at this tree graph, we can see that for any two of these nodes, there's only one path between them. And we can see that each one of these nodes has a single parent. The root node is the node that has no parents, and a leaf node is a node that has no children. So this is one type of graph, and note that there is only one way to get from the root node to any other node in this graph. So there are no cycles, there are no loops, there's only one way to get from one node to another node. So for example, to get from this node up to the root node, the only way to do that is to go to this node's parent and then to that node's parent. So we can only traverse this single connection between each node. One practical example of a tree graph is a computer file system. So in a computer file system, each file or directory has a single parent directory. And in order to get to any of the nodes in a file system, there's only one way to get there. So in order to get to the docs directory, we have to go through the home directory and then to the Eli directory and then to the docs directory. There's no other way to get there. Another special type of tree graph is a binary search tree. In a binary search tree, there's another rule that says that the left node is always less than its parent node, and the right node is always greater than its parent node. So if we look at this example, we have a root node of 5. So anything to the left of the 5 must be less than 5. So the 1, 2, 3, 4 are all nodes that we see to the left of 5, and those are all less than 5. And then any nodes to the right of the 5 must be greater than the 5. So here we see that the 6 is on the right of the 5, and that's true for each one of these nodes. So if we move down to the node with 2, the node to its left is 1, it's less than 2, and the nodes to the right are greater than 2. So we can use this type of tree to perform a binary search. So for example, if we were searching for the value 3, we would start at the root node and we would ask the question, does this node equal the value I'm searching for? Does 5 equal 3? And the answer is no. So then we would ask, is the value we're searching for less than or greater than this node? And we would see 3 is less than. That means that we could discard the whole right side of the tree from this node and move down to the left side. And then we would compare the 3 to 2. we would see that it's greater, so we would discard the whole left side of the tree from this point, and the next value we look at would be 3. So we are familiar with this algorithm, this binary search algorithm, and you can see that if we represent the nodes in a graph, we're discarding half of the upper half or lower half of the tree with each iteration. Graphs are very nice visual representations of data, but we can't really represent a visual graph programmatically in our source code. So we're going to talk about 2 other ways to represent data in a graph. And probably the most useful way is something called an adjacency matrix, or just a matrix. Really, this we can think of also as a table. So we have a 2 by 2 matrix. I'm sorry, not a 2 by 2 matrix, but a two-dimensional data structure. So that's why we call it a matrix. But tables are also two-dimensional data structures. And each row in this table or matrix is represented. We have 1 row for each node, and likewise we have 1 column for each node. And the rows represent the origin node, and the columns represent the destination node. So the way that we fill in this matrix is we look at each node. We'll start with node A, and we look at all the nodes we can get to directly from A. And since this is an unweighted graph, we're going to note our edges in our matrix with 0s and 1s. So if there is an edge, we put a 1, and if there is not an edge, we put a 0. So in this case, we've got an edge that goes from A to B. So in the row for A, we put a 1 in the B column, and that indicates that we have an edge that goes from A to B. Now if we look at A, there are no other edges that go from A to another node. We have some edges that come into A from other nodes, but no edges that take us from A to any other node. So for the rest of the columns, we put 0 because there are no other edges. Next we go to B, and we see that from B we can get to A, we can get to D. So we put a 1 in the column for A, and we put a 1 in the column for D, and we put 0s in the columns for B and C. From B we can't get to ourselves, and we cannot get directly to C. Next we move on to C, and we see that from node C we have an edge to A and we have an edge to D. So we mark those edges with 1s in our matrix, and we put 0s for the other 2 nodes. And then finally from D, we can see that we can only get to B from D. So we put a 1 for the B column to indicate we have an edge there, and a 0 in the rest of the columns. So representing our data this way in a matrix would be represented in our program as a two-dimensional array, and that would be easier for us. We could deal with that data structure in order to examine the data in our graph and operate through that data. Now, if our graph has weights on it, so we have a weighted graph, then we still represent edges the same way. It's just that we use the weighting instead of the number 1. So in this example, we have a weighted, undirected graph. There are no arrows in this graph, so it's undirected, and that means the edges go in both directions. So if we start with A, from A we can get to B, and it cost us 2, so we put a 2 in the B column. We can also get to C, and it cost us 3, so we put a 3 in the C column. And we can get to D from A with a cost of 4, so we put a 4 in the D column. Next we move on to B, and from B we can see that we can get to A with a cost of 2, and we can get to D with a cost of 5. So we put a 2 in the A column, a 5 in the D column, and a 0 in the other columns. Then from C we can get to A with a cost of 3, so we put the 3 in the A column. We can get to D with a cost of 2, so we put a 2 in the D column, and 0s in the other columns. Finally, in D, from D, we can get to B, A, or C with the cost of 4 to A, 5 to B, and 2 to C. So we put 4 in the A column, 5 in the B column, 2 in the C column. Another way that we can represent the data in our graph is using an edge list or an adjacency list. So this is simply a list of edges in our graph. If we have an unweighted graph, then we can just specify the edges, origin followed by destination, and it could be any kind of comma-separated list. Here I've shown it in square brackets, but it could be represented some other way. The important parts are that we represent pairs of nodes. If there's no weighting, we don't have any numbers represented in those pairs, and we always list the origin node first and the destination node second. So in this graph, we have a path from A to B, we have a path from B to A, and from B to D. We also have a path from C to A and C to D, and we have a path from D to B. So we represent each one of those edges. We can count the edges, 1, 2, 3, 4, 5, 6, and we should have the same number of elements in our list, 1, 2, 3, 4, 5, 6. So that's a way that we can check to make sure that we got all of the edges. Now, if what we have is a weighted graph, we have to include the weights in the list as well. And we could either do that by putting the number between the origin and destination, as is done here, or we could put the weight in front of the pair of edges or after the pair of edges. You'll see it all of those ways potentially, and it doesn't matter where you put the number in the representation of the edge as long as it's there. And it's still true that the origin node comes first and the destination node comes second. Now this graph is also undirected, and that means we need to represent the edge in both directions. So we have to represent A and B, the path from A to B with a weight of 2, and we also have to represent the path from B to A with a weight of 2. So we have A to B and B to A. So for each one of these edges, we'll have 2 different representations of the edge in both directions. So we have A3C and C3A, and so on. So if we have an undirected graph, then we'll have 2 items in the list for each edge. So here we have 1, 2, 3, 4, 5 edges. So we should have 10 elements in our list. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's a way that we can check to make sure we have the correct number of items in our list. In addition to drawing lists or matrices from graphs, we also need to be able to draw a graph from a list or a matrix. So let's look at this example with an edge list first. Here we have an edge list. What can we tell about this edge list? Is our graph directed? Is it weighted? Well, the easiest one to answer is whether or not it's weighted. There are no numbers represented in this edge list, so it's not weighted. Is it directed? Well, in order for it to be directed, if it's directed, that means that we have some paths that are not, that don't go, some edges that don't go in both directions. So if it's undirected, it means that we have an edge in both directions for every edge. So let's draw the graph to see if that's true. In order for it to be undirected, if there's an AB, there must also be a BA. So we could actually quickly look and see that there's not a BA to go with this AB. So it is a directed graph in that case, because that means that we don't have edges going in both directions in all cases. So let's try to draw this graph. So I would start by just trying to draw edges. So I know I have a node A that's connected to a node B, and the connection goes from A to B. So I'll draw that edge, that's this one. Now we also have A connected to E. So let's draw an E, and A points to E. The edge goes from A to E. So there we go, that's that one. And then we also have B connected to C. So let's draw the edge between B and C. And then we have C connected to a D. And the edge goes from C to D. That's that one. And then we also have E connected to B. So we'll draw that connection from E to B. And there we go. That is a graph representation of that list. It's also important to know how to draw a graph from a matrix. So if we have a matrix like the one shown here, let's see if we can draw the graph. So we'll start with A. So I'm going to draw a node A. And I can see that it's connected to B. And I don't know yet if it's directed or not. So I'm going to draw an arrow. And A to B, I can see we have a weighted graph. There's a weight of 3. So I'm going to put the 3 on that edge. Now I also have a path from A to C. I'm going to draw that path, and it has a weight of 1. And then I have, that's all that I have for A. So that's my 3 and my 1. Next, I have a path from B to A. So this one goes in both directions, and it also has a weight of 3. So this is the way that I'm going to draw it. For now, it indicates the direction goes both ways, and the 3 is the weight for both. And in the end, if I have two-sided, two arrows on each edge, then I know that it's an undirected graph, and I can remove the arrows. But I'm just going to go through and check. So there's my B to A. Then I also have a B to C with a weight of 7. And I have a B to D with a weight of 5. So that takes care of B. Now from C, I have an edge from C to A with a weight of 1. So I'm just going to draw the other arrow on that side since it's the same. And then I also have an edge from C to B with a weight of 7. So I'm just going to draw the other arrow on that one. And then I have an edge from C to D with a weight of 2. That takes care of C. Then D, I have an edge from D to B with a weight of 5. So I'm just going to draw the other arrow. And then from D to C with a weight of 2. And then I also have an edge from D to E with a weight of 7. Finally, from E, I have an edge from, look at this, I forgot one, from B to E with a weight of 1. So it's handy to put those little check marks, isn't it? And then from E to B, I also have an edge of 1. So that one is also bidirectional. And E to D with 7. So now that I can see that all of my edges are bidirectional, I could actually remove all of the arrows, because what we have here is an undirected graph, and there's going to be no easy way for me to do this in my drawing pad. So let me fix this up. Now I've removed all of my arrows. We can see here that we have a weighted, undirected graph. So I could have looked through my matrix and worked out that it was undirected, but I like to draw the graph and work it out that way. You can do what works best for you. And sometimes when we draw a graph from a matrix or a list, it doesn't come out as nicely as this. Now, I knew what this graph was going to look like because I made the matrix and I knew what to expect. But if you find that the graph you draw initially isn't clear, if there are lines overlapping, or you have to make big arcs to draw the edges, then you can always redraw your graph after the first time. So why would we want to go from a matrix to a graph? Well, one reason that we might do that is if we wanted to apply Dijkstra's algorithm to find the shortest path. So let's talk about Dijkstra's algorithm. Now, this slide describes the steps of Dijkstra's algorithm, and I'm not going to go through this slide. I'm going to demonstrate applying the algorithm, but it's there for your reference so you can look back at it later. But I'm going to tell you that we use Dijkstra's algorithm to find the shortest path between one node to every other node in a weighted graph. So this algorithm is appropriate when we know the origin node and we want to find the shortest path to some other node or to multiple other nodes. When we apply Dijkstra's algorithm, we will know the shortest path from the origin node to every other node that it can reach in the graph. So let's see how we apply this algorithm on the graph that we just drew. Here is our graph from the last example. So let's say, for instance, that we wanted to find the shortest path from C to E. So the shortest path C to E. Now, if we had a graph of this size, we could use brute force and we could work it out. But if we had a graph with 10 nodes or 20 nodes or 100 nodes, we would want to have some systematic way that we could program to find the shortest path so that we wouldn't make any mistakes. We'd want to know some deterministic method for finding the shortest path, and Dijkstra's algorithm is a good algorithm to do this. So let's practice it with this graph. So for Dijkstra's algorithm, the first step is that we assign initial costs to each node, starting from the origin. So in this case, our origin is C, so we start from C, and the cost to get from C to C is just 0. Now, until we've applied the steps of the algorithm, we don't know the cost to get to the other nodes, and we start by assigning the maximum possible value for cost to each node, and we're just going to use infinity. So infinity is what we assign as the cost to get to every other node initially. So this is where we start. So that's step 1, is to assign initial cost to each node, 0 for the origin node, infinity for all of the other nodes. The next step of the algorithm is that starting from the origin, we adjust the cost for each node that we can get to from this node. So from C, we can get to A, for example, and the cost to get to A is 1. So we ask the question, is 1 less than the current cost assigned to A? The current cost assigned to A is infinity. 1 is less than infinity, so we replace that cost with the updated cost 1, and we indicate which node we got to A from with that cost of 1, so C. So we got to A, the cost of 1 from C. Then we do that for the other nodes we can get to from C. So from C, we can also get to D with a cost of 2. So we replace infinity with 2C. And from C, we can get to B with a cost of 7. 7's less than infinity, so we replace infinity with 7C. Once we've done that, we have considered all of the edges from C. So we mark C as done. So I'm just going to put a green dot on C to indicate that we are done with C. In Dijkstra's algorithm, we call that a visited node. Once we have calculated all cost from a node, we say that that node is visited, and we no longer consider it in any calculations or further steps in the algorithm. So the next step of the algorithm is to move to a child of the current node that we just finished, and we choose the child with the smallest cost at this point. So if we look at the children of C, we have A, B, and D. So if we look at A, B, and D, the one with the smallest current cost is A. it has a cost of 1 assigned to it, B has a cost of 7, and D has a cost of 2. So if we have two children that have the same current cost, we just pick one. But we have a clear lowest cost now, it's A. So now we're going to move to A, and we're going to do the same steps that we just did for C. So there's only one node we can get to from A, and that's B. And to calculate the cost to get to B, we have to add the edge cost plus the current cost on A. So it's 1 plus 3, which is 4. And we ask, is 4 less than the current cost on B? And it is. So we're going to replace this 7C with 4. And we got that 4 going from A and then C. So we put the A because we came from A, but we see from A we came from C. So we also include the C there. So 4A, C. Now that we've updated the cost on B, there is no other path from A. The only other path from A goes to C, but this node has already been visited, so we don't consider any paths to nodes that have already been visited. So that means we're done with A. I'm going to mark A as done with a little green dot. So now we'll no longer consider A in any of the further steps of the algorithm. So next, we look at the next child of C, the node that we were on, that has the next lowest value. So we did A. A had a cost of 1. The next smallest one is D, which has a cost of 2. So now we move to D. And from D, we ignore the path to C because it's already been visited, but we can consider the paths to B and to E. So from D to B, the cost is 5 plus the 2. So the cost from D to B is 7. And 7 is not less than the current cost on B, 4. So we don't make any changes to the cost on B. And we are done considering that path. Next, we look at the path from D to E, which cost 7 plus the 2, so that's 9. 9 is less than infinity, which is the current cost on node E. So we cross out the cost on E, infinity, and we replace that with 9. That 9 came from D. And from D, we came from C. So we make sure that we include both of those. And now we're done with D. So we can put a green dot on D. So next, we will look at B because B is the final child of C. It has not been dealt with yet. So from B, there are several places we can go, but most of them are irrelevant because from B we can get to A, but A's already been visited. And from B we can get to C, but C's already been visited. And from B we can get to D, and D's already been visited. So the only path we need to consider is from B to E. And the cost from B to E is 1 plus the 4 that's already on B, so that's 5. 5 is less than 9, so we're going to replace this cost. Let me change my pen color. We'll replace this cost with 5, and that's coming from B, which already has an A and a C on it. So we're going to add A and C. And that takes care of B. We can mark B as done. And we have E, but since all the other nodes that we can get to from B, from E, which are B and D, are done, we're done with E. So now we're finished with the algorithm. And what we have when we're done is the shortest path from our origin node, C, to any other node in the graph. So for example, if we wanted to know the shortest path from C to E, all we have to do is look at this value that we ended up with on E. The number part tells us the cost. So the cost is 5, and the path is given to us by the letters that we've recorded, and we have to end with E, of course. So the path and we put this backwards, is C, A, B, E. So we go C, A, B, E to get that shortest path of 5. So we could also see that the shortest path to every other node, which is straightforward in this case because there are direct lines to those other nodes, but from C to A, the shortest path is 1 directly from C. To B, the shortest path is through A, and it costs 4. To D, the shortest path is directly from C, and it costs 2. So this is Dijkstra's algorithm. We apply it the same way every time, and it's a good and challenging exercise to try to write this algorithm out in code, teach the computer how to perform this algorithm. It's not simple. It requires some somewhat sophisticated data structures to keep track of all the information we need to keep track of, but it really does have you firmly and fully understand this algorithm. You could also just practice it. If you practice it a few times, you'll get the hang of it. And there are some other videos that you can watch and other sources of information that explain the algorithm in different ways. So Dijkstra's algorithm is very useful. It's a very popular algorithm, and it's fairly simple to apply once you understand the steps, but it's not always appropriate. So it's only appropriate when there's no requirement to visit all nodes and we have an origin node. It is not appropriate if we need to find the shortest path that visits all nodes, or when no specific origin node is given. In other words, we're allowed to start our path from any node. Then finding the shortest path would require that we would apply Dijkstra's to every node, and that might not be the most efficient way to do things. So we use Dijkstra for finding the shortest path when a specific origin is given and there's no requirement to visit all nodes. Sometimes the problem we're given, though, is to find the shortest path that visits all nodes. And this is a really challenging problem in mathematics and computer science, and it hasn't really been solved very well. So there are some algorithms out there that will solve this problem in many cases, but there are always either some corner cases or the algorithm is too complex for large numbers of nodes. So there's a limit to the number of nodes that we can apply the algorithm to in any practical way. So when we're asked to find the shortest path that visits all nodes, if the graph is small enough, then often the simplest way to do it is just using a brute force method. So that just means that we check all the paths that visit all the nodes and we find the least expensive path. Let's look at an example of trying to find the shortest path that visits all nodes. This is also sometimes referred to as the traveling salesman problem. So generally when we have this problem, we can start from any node, and the only rule is that we have to visit every node. Sometimes there's a variation of this problem where we have to return to the point of origin, but we're not going to consider that case now. We're just going to consider the case that we need to visit every node in this graph, and it doesn't matter what order we do it in, so we don't have to start at any particular node. Now, when we look at this graph, we see that it is a undirected graph, so all the edges go in both directions. And we could start by looking at the graph and seeing that we have some expensive edges here. So the 7 and the 6 are expensive edges. And if there's a way to avoid those, then we may end up with a more efficient path. So if, for example, we just went around the outside, so we went A, B, E, D, C, then that would cost us 3 plus 1 plus 7 plus 2. And that is 13. Well, we could see that it would cost us 1 less if we took this 6 path instead of this 7 path. So let's have a look at that. If we instead we went around this way and we went A, C, D, E, B, that's not quite right. That's not what I wanted to do. If we avoided this 7, so if we went, let's say, E, B, A, C, D, and then we're avoiding that 7 edge, so that one would cost us 1 plus 3 plus 6 plus 2, and that is 1 cheaper, so that cost us 12. But we're still not avoiding this expensive 6 edge. So in order to avoid those outer edges, we're going to have to use the inner edges. So let's think about ways that we could use the inner edges. So we could, for example, we could go E, B, D, C, A. And this avoids the 7 and the 3. We do a little bit better there. We get 1 plus 2 plus 2 plus 6. And that gives us 11. So that's a little bit better. But we still aren't avoiding the 6 edge. So let's see if we can do better than that. What if we went D to C to B to E, back to B, and then to A. So even though we're visiting B twice, when we visit B twice, we're only going across this 1 cost path twice. So let's see what that looks like. So D to C would cost 2, C to B cost 1, B to E cost 1, E back to B cost 1, and then B to A cost 3, and that gives us 8. And then there's one more path that's here that has the same cost, and it goes from A to B to E, back to B, to A to B to E, back to B, and then we can take the C path and then to D. So in this case we get A to B is 3, B to E is 1, E back to B is 1, B to C is 1, and C to D, 1, not C, and C to D is 2, which also gives us 8. And you'll find that that's the most efficient. Either one of these paths costs the same, so either one of those would give us the most efficient path. So that was the first one here is D, C, B, E, B, A, and the second one we did just now was A, B, E, B, C, D, and both of these will give us a value of 8. So this slide shows some other paths and points out the 2 paths that we just found provide the shortest path between all nodes. So my suggestion is to practice this as well on some graphs, and you'll get some feeling for how to look for the shortest path, but it really is just a brute force method that you apply. You need to make sure that you add those values up correctly, and again, this is only going to work if you have a reasonably sized graph. If your graph gets much larger, this problem gets to be really difficult. And if you're keen, you could take on trying to find an algorithm that works, and you'll become famous because no one's been able to do a really good job of it so far. So that's all that there is that we'll cover about graphs. The key here is to practice the terminology and to practice the algorithms like Dijkstra's algorithm, and practice drawing matrices from graphs and graphs from matrices and so forth, and you'll be fine.